Welcome to EDU World Space.
So we want to find the tension in the crane's cable, uh, and we can say that the tension in the cable plus the buoyant force would be equal to the weight of the ship. So we can say that the tension would be equal to the weight of the ship minus the buoyant force. And so we can say that this is going to be, the tension is going to be equal to the mass of the hull times G minus the density of water times the volume that is submerged underneath the water times the acceleration due to gravity. And so T is going to be equal to the mass of the hull times G minus the density of the water. The volume submerged would simply be the mass of the hull times G. And then again, the volume submerged would simply be the mass of the hull divided by the density of the hull. And this is going to equal the mass of the hull times G times 1 minus the density of water divided by the density of the hull. And so we find that T, the tension in the cable, will be 1.6 times 10 to the fourth kilograms times 9.8 meters per second squared times 1 minus 1,000, the density of water, divided by the density of the hull, 7,800 kilograms per cubic meter. And we find that the tension in the cable is going to be 1.367 times 10 to the fifth newtons. So this is when essentially the hull is a good a percentage of the hull's volume is underwater. And this would be the answer for part A. For part B, however, now the entire ship is out of the water. So that means that the tension, again, when a hull is completely out of water, that means that there isn't any buoyant force in order to help the cable. So essentially, the tension in the cable would be equal to the total weight of the ship. So this would be equal to 1.6 times 10 to the fourth kilograms, and then times 9.8 meters per second squared. And we find that the tension when the ship is completely out of the water is going to be equal to 1.568 times 10 to the fifth newtons. And this will be our final answer for part B. That is the end of the solution. Thank you for watching.